This molecule could cure cancer, but finding it requires testing 10 to the power of 47 combinations. The world's fastest supercomputer would need longer than the age of the universe to check them all. On October 22, 2025, this machine did it in minutes. Not by calculating faster, by calculating differently. By existing in every possibility at once. Every computer you've ever used thinks in binary. On or off, 0 or 1, yes or no. Your laptop has billions of these switches, each one deciding 0 or 1. Classical computers are fast, extraordinarily fast, but they're still fundamentally limited. Here's caffeine, 24 atoms. A classical computer can simulate how these atoms interact. It checks each possible configuration, one at a time. Aspirin, 21 atoms, still manageable. Penicillin, 41 atoms, and suddenly we hit a wall. Each new atom doesn't add complexity, it multiplies it, exponentially. By the time you reach a molecule with just 60 atoms, the number of possible configurations exceeds the number of atoms in the observable universe. This is KRAS, one of the most mutated genes in cancer. For decades, scientists called it undruggable. In 1982, researchers first identified KRAS mutations in cancer cells. 43 years later, we still can't drug most of them effectively. Not for lack of trying. Pharmaceutical companies spent billions, tested tens of thousands of molecules. Every approach hit the same wall. The binding pocket on KRAS, the spot where a drug needs to attach, is shallow, smooth, featureless, like trying to grip a wet bar of soap. Other proteins have deep grooves where drugs can nestle. KRAS doesn't. And it gets worse. KRAS is flexible. It changes shape constantly. Water molecules crowd the binding site. Electrostatic forces shift unpredictably. And at the atomic level, the physics becomes quantum. Electrons aren't in fixed positions. They're in clouds of probability. Bonds don't stay rigid. They vibrate, bend, break, reform. Quantum tunneling allows particles to pass through barriers they shouldn't be able to cross. To predict whether a drug will work, you need to simulate all of this, quantum mechanically. Every electron, every water molecule, every vibrational mode, every possible configuration. Classical computers approximate, simplify, make educated guesses. They're often wrong. That's why, for 30 years, KRAS remained undruggable. Not because we didn't understand it, because we couldn't calculate it precisely enough. And millions of people with KRAS-driven pancreatic cancer, lung cancer, colorectal cancer, kept waiting for a cure that required physics we couldn't simulate. Until 2025. A classical bit is binary, 0 or 1. A quantum bit, a qubit, is both, at the same time. It sounds impossible because it violates every intuition we have about reality. But at the quantum scale, particles don't exist in definite states. They exist in superposition. All possibilities, simultaneously, until you measure them. You've heard the thought experiment, Schrödinger's cat, alive and dead at once. It sounds like philosophy. It's physics. And in 2025, we can control it. This is a single atom, trapped by lasers, cooled to near absolute zero. Its electron spin is our qubit, and when we put it in superposition, it's not 0 or 1. It's exploring both paths through the computation at once. With 2 classical bits, you have 4 possible states: 0, 0, 0, 1, 1, 0, 1, 1. Your computer checks them one at a time. With 2 qubits in superposition, they exist in all 4 states simultaneously. 3 qubits, 8 states at once. 10 qubits, 1,024 states at once. 50 qubits, more states than all the classical computers on Earth could store. 100 qubits, more simultaneous calculations than there are atoms in the observable universe. But superposition is only half the story. The other half is entanglement. When 2 qubits become entangled, they're no longer independent. Measure one, and you instantly know something about the other, even if they're separated by light years. Einstein called it spooky action at a distance. He hated it. He was also wrong. Entanglement is real, verified, repeatable. And it's what makes quantum computers capable of solving impossible problems. Not all problems are created equal. Some are easy: addition, sorting, searching databases. Classical computers excel here. Others are exponentially hard. Every additional variable doesn't add difficulty, it multiplies it. Simulating molecules, optimizing supply chains, breaking encryption. These problems grow so fast that classical computers hit a wall. Quantum computers don't climb the mountain faster. They take a fundamentally different path. They use superposition to explore multiple routes simultaneously. They use entanglement to correlate information across the computation. They use interference to amplify correct answers and cancel wrong ones. Like waves on water, peaks adding, troughs canceling, quantum computers guide probability toward the solution. For 30 years, quantum computing was a beautiful idea that didn't work. Qubits were too fragile. They interacted with their environment: heat, vibrations, stray electromagnetic fields. And within milliseconds, the quantum information collapsed. By the early 2000s, many physicists thought it might be impossible. Not theoretically, practically. They were wrong. This is Willow, Google's 105-qubit quantum processor, unveiled in December 2024. It operates at 15 millikelvin, colder than interstellar space, so cold that atoms barely vibrate. Each qubit is a superconducting circuit, a loop of niobium where current flows without resistance, creating quantum states that can be precisely controlled. And Willow did something no quantum computer had done before. It reduced errors exponentially as it scaled up. That sounds technical. It's revolutionary. The breakthrough happened on a Tuesday morning, April 16, 2024. The team was testing a new error correction code, something called a surface code architecture. The idea: arrange qubits in a grid. Some qubits hold your data, your actual computation. Others constantly check for errors, like spell checkers monitoring your typing in real time. When an error appears, a qubit flipping state, decoherence creeping in, the system detects it, corrects it, before it spreads. before it destroys your calculation. But there's a problem. Error correction requires more qubits. More qubits mean more things that can go wrong. More connections, more noise, more opportunities for errors to cascade. Every previous attempt saw error rates increase as systems scaled up. You'd add qubits to fix errors and create more errors in the process. 2 steps forward, 3 steps back. Theoretically, if you could get error rates low enough, below a critical threshold, adding more qubits would improve performance exponentially. But no one had ever crossed that threshold. Not in 30 years of trying. On April 16th, they ran the test. Started with a small grid, 3 by 3 qubits. Measured error rate. Then scaled up, 5 by 5 qubits. The error rate dropped. They checked the equipment, ran it again. Same result. Scaled to 7 by 7 qubits. Error rate dropped again. Not linearly, exponentially. Julian Kelly, lead quantum hardware engineer, later described the moment. We sat there looking at the data for probably 20 minutes, just staring. Because if this held, it meant we'd crossed the threshold, the thing we'd been chasing for decades. It held. They ran the experiment dozens of times, different configurations, different error types. Every time, as they added more qubits, errors decreased. They'd crossed the error correction threshold, the point where quantum computers can correct errors faster than they create them. With classical computers, more components mean more errors accumulating. With Willow, more qubits meant better error suppression. Physicists had pursued this for 30 years. On a Tuesday morning in April, it finally worked. They spent 8 months verifying, testing, documenting. In December 2024, they published. And suddenly, scaling quantum computers wasn't a physics problem anymore. It was an engineering problem. The path to millions of qubits, to fault-tolerant, universal quantum computing, was finally open. 10 months later, October 22nd, 2025. Google published something extraordinary, an algorithm called quantum echoes, running on Willow, solving a real-world physics problem. The task: measure how information spreads and scrambles in a highly entangled quantum system, something called an out-of-time order correlator, or OTOC. It's the kind of calculation you'd need to understand molecular dynamics, how drugs bind to proteins, how materials conduct heat, how quantum systems evolve. The world's fastest classical supercomputer, Frontier, would need 3 years per data point. Willow did it in seconds. 13,000 times faster. Hours versus years. This is the first time in history any quantum computer has successfully run a verifiable algorithm that surpasses the ability of supercomputers. Verifiable. That's the key word. The algorithm can be repeated on different quantum hardware. The answer can be checked experimentally in nature. This isn't a benchmark test. It's a real-world calculation with real-world applications. Remember KRAS, the undruggable cancer protein? In April 2025, researchers at In Silico Medicine and the University of Toronto did something remarkable. They combined quantum computing with machine learning to design KRAS inhibitors. The quantum system screened 100 million potential drug molecules, refined them to 1.1 million candidates. The team synthesized 15 of the most promising. 2 of them worked. One compound, ISM 061-018-2, showed real biological activity against KRAS-G12D, a mutation that drives some of the deadliest cancers. At St. Jude Children's Research Hospital, quantum-enhanced machine learning generated antiviral compounds. All 12 candidates showed activity against hepatitis C and human coronavirus. 100% hit rate. Every single molecule worked. In classical drug discovery, a 5 to 10% hit rate is considered excellent. The difference? Quantum computers model the actual quantum behavior of electrons in molecules. Not approximations, not simplifications. The real physics. We're not just building faster computers. In 1981, physicist Richard Feynman proposed an idea. Nature isn't classical, so if you want to simulate nature, you need a quantum computer. 44 years later, we're proving him right. Google isn't alone. IBM unveiled Condor, 1,121 qubits, though they haven't yet demonstrated quantum advantage on practical tasks. In November 2025, Quantinuum launched Helios, claiming the most accurate commercial quantum computer available. IonQ, using trapped ions instead of superconducting circuits, achieved quantum advantage in drug discovery and chemistry simulations. China's Zhujiang 4.0 photonic quantum computer completed a calculation that would take classical supercomputers longer than the age of the universe, specifically 1,000,000,000,000,000,000,000 years. D-Wave's quantum annealers simulate magnetic materials, realizing Feynman's original vision of using quantum systems to understand quantum nature. Different technologies, different approaches, superconducting circuits, trapped ions, photons, quantum annealing. Each breakthrough accelerates the others. This isn't a winner-take-all race. It's collective progress toward the same impossible goal. Drug discovery is just the beginning. Quantum computers are designing better batteries, simulating how ions move through materials at the quantum level. Catalysts for carbon capture, materials for fusion reactors, superconductors that work at higher temperatures. And then there's AI. Quantinuum's generative quantum AI combines quantum computing with machine learning, using quantum-generated data to train AI models that would be impossible classically. The AI doesn't just learn from classical data, it learns from quantum-simulated molecular spaces, chemical configurations that have never existed, but could. Climate modeling, weather prediction, financial optimization, logistics, supply chains, traffic flow. Any problem where you need to explore vast possibility spaces, quantum computers offer a fundamentally new path. But let's be honest about what still doesn't work. These machines require infrastructure classical computers don't, cooling systems that reach near absolute zero, vibration isolation, electromagnetic shielding. We have 105 qubits. We need millions for fault-tolerant universal quantum computing. Error rates are improving, down to 0.000015% per operation, but they're still not zero. We have a handful of quantum algorithms. We need thousands. Each problem requires custom quantum circuits. IBM's roadmap targets fault-tolerant quantum computing by 2029. DARPA is betting on utility-scale quantum by 2033. Google suggests real-world applications within 5 years, which means soon, but not yet. And some researchers urge caution. NVIDIA CEO Jensen Huang said in January 2025 that quantum computing is still 15 to 30 years from being truly useful. The industry spent the year trying to prove him wrong. They might be succeeding. But maybe the deeper question isn't, when will quantum computers be useful? Maybe it's, What does it mean that nature itself is quantum? For all of human history, we've thought in classical terms. Objects are in one place or another. Cause precedes effect. Information can't travel faster than light. Quantum mechanics says, objects are everywhere until measured. Entangled particles share information instantaneously. Particles tunnel through barriers they shouldn't be able to cross. Building quantum computers isn't just engineering, it's philosophy. Because when you simulate a molecule with 60 atoms on a quantum computer, you're not approximating it. You're recreating the actual quantum physics. You're using one piece of quantum reality to understand another. Which raises a question no one's quite ready to answer. If reality is quantum, have we been thinking about computation wrong all along? That molecule we started with, the one that could cure cancer, but would take supercomputers 47 years to find. In 2025, quantum computers found it in hours. Not because they calculated faster, because they calculated like nature does. Superposition, entanglement, interference. Nature has been using quantum computing for 13.8 billion years. We're just now learning the language. By 2030, quantum computers might design most new drugs. By 2040, they might optimize global supply chains, model climate systems, accelerate AI beyond recognition. Or they might solve problems we haven't imagined yet, materials that don't exist, medicines for diseases we can't treat, energy systems that seem impossible today. The quantum revolution isn't coming. It's here. 12 quantum computers worldwide are solving real problems, with real applications, with verifiable results. For centuries, we've bent nature to our will, built tools from stone, steel, silicon. Quantum computing is different. We're not imposing our logic on nature. We're learning to compute the way nature does. And if we get it right, if we build machines that think like the universe thinks, there's no limit to what becomes possible. This is Cosmic Canvas, where we explore the universe's operating system. Until next time, stay curious. The impossible is becoming routine.